This example comes in two parts, so let's tackle each part individually. First, we are asked to consider two masses that are placed 3 centimeters apart. The gravitational force between them is then measured. We don't know what it is, but let's call it F. Now those masses are moved closer together so that they are only 1 centimeter apart. And the question is, how does the gravitational force change? Well, to figure that out, we need to figure out how the distance changed. We know the distance changed, but how did it change? Was it multiplied by a number or divided by a number? That's what we have to figure out. Well, the distance went from 3 centimeters to 1 centimeter, so it was divided by 3. Now remember, gravitational force is inversely proportional to the square of the distance. So that means whatever I did to the distance, I have to do the opposite to the force, and I have to square it. So if the distance was divided by 3, the force must be multiplied by 3 squared. Well, 3 squared is 9, so that means the force must be multiplied by 9. In other words, the new force is 9 times stronger than the old force. So notice what we did here. We figured out what the distance was multiplied or divided by. Then we did the opposite to the force and we squared it. Distance was divided by 3, so force was multiplied by 3 squared, or 9. Okay, now let's look at the second part of the example. In this part of the example, we're considering two objects that are placed 5 centimeters apart from each other. Once again, the gravitational force between them is measured. We don't know what it is, but we'll call it F. Now this time, rather than changing the distance between the objects, we're going to change the objects themselves. We're going to take the first object and replace it with an object that has half the mass. In other words, the mass of the first object is divided by 2. Now remember, the gravitational force is directly proportional to the mass involved. Thus, whatever we do to mass, we must also do to force. Since the mass was divided by 2, that means the force must be divided by 2 as well. Therefore, the new force is equal to the old force divided by 2. Well, we're not quite done yet, because the other object is changed too. According to the problem, the other object gets replaced by an object that is 8 times as massive. In other words, the mass of the second object is multiplied by 8. Well, once again, anything we do to the mass, we must also do to the force. Therefore, if the mass is multiplied by 8, the force is multiplied by 8 as well. What can we say about the new force then? Well, remember, the first mass was divided by 2, and therefore the new force was the old force divided by 2. This mass is multiplied by 8, so we must now further multiply that by 8. So the new force is the old force divided by 2, because of what happened with the first mass, times 8, because of what happened with the second mass. Well, if I take a number, divide by 2, and then multiply by 8, what's the net effect? Well, the net effect is to multiply by 4. If I divide by 2 and then multiply by 8, that's the same as multiplying by 4. Therefore, the new force is 4 times the old force.